interpolation error. That is, if we are approximating, if we are finding the approximation of the function at some point, say x, then what is the error in this approximation? That is, it is going to be fx minus pnx, where these yi's we are taking it as f of xi, right? So what is this Lagrange interpolation error? So we obtain this formula with this assumption that f is n plus 1 times continuously differentiable on the interval containing all the xi's and the point x where we are finding the approximation, right? So then we obtain this formula that the interpolation error is given by this factor divided by factorial n plus 1 into n plus 1.
F n plus 1 xi.
Yes, so where xi lies between. So xi is any point in this interval. If we call this as I, so xi lies in this interval I. Okay. So theoretically, this LJX has very nice properties, and like you can, for a small data, you can use very easily, you can compute this LIX and find the PNX, right? But there's a drawback with this form of the interpolating polynomial. And what is that drawback? So suppose we are given the data set of length. Okay, suppose we have, so you're getting some data. So you have the xi's and yi's. Say up to xk. Okay, so you can find your Lagrange interpolating polynomial using this set of data. So suppose we have found pk of x, right? So this will involve, so let me write it explicitly what this is going to be. So this is going to be summation of LJX into
yj.
yj, and j is varying from 0 to
K.
And note that these LJX, these are again polynomials. So what are these LJX? They are going to be the product of all x minus xi divided by xj minus xi. I is ranging from 0 to k, and I is not equal to j, right? So note that these products are like basically what is a numerator? Numerator is like all the combinations or the product of all x minus xi's except the term x minus xj, right? And denominator is the difference of xj and xi, where I is varying from 0 to k, and I is not equal to j. So you don't have the factor 0 here. Okay, so we are having the denominator in this way. Okay, so now if you include one more data points, suppose you have already computed all these LJ's x, right, with this set of data points. And if we include one more, suppose we got the information of one more data points, that is at the xk plus 1, this function takes the value yk plus 1. Okay, so now can we use already computed this LJX? We cannot use it because you have, these are the products of all x minus xi, so you have to recompute all of them, right, for this new set of data, because you have to, your products will consist of one more term in this case, right? So because of this reason, it is not practically, these Lagrange interpolating form is not so convenient, because you cannot go from say you are already on one polynomial, and suppose you want to find another polynomial of degree 1 greater than the existing polynomial, then it is not convenient to go from like one lower degree to the one higher degree. Okay, so now we are going to see another form of the interpolating polynomial which will solve this problem. So that we call it as Newton's form of interpolating polynomial. So basically, we are again going to find the interpolating polynomial, but it's just that we will have it written in a different form. Okay. So what is the idea behind this new form? So the same thing, that suppose we already know, let's say Pn minus 1x. Okay, and I want to use this. That is, this is a interpolating polynomial of degree less than equal to n minus 1, and the interpolation data is we have xi, yi, I is ranging from 0 to n minus 1. Okay, so I want to use this to construct the polynomial of 1 degree higher. That is, say I want to construct Pnx here. Okay, so the idea is, so this I'm going to use the same idea which we used in proving the existence and uniqueness of the interpolating polynomial. That is, I'm going to use this Pn minus 1x. Okay, and since this is a polynomial of degree less than equal to n minus 1, and I want to construct a polynomial of degree 1 higher, so I'm going to add one term which we have to determine. Now what this term has to be? So you can note that this is a polynomial of degree less than equal to n minus 1, and I want this to be a polynomial of degree less than equal to n. So this Cx again has to be a polynomial, right? So Cx here is polynomial of degree n. And note that what are the properties we are seeking for the Pnx. So we are seeking that Pn at xi should be equal to yi for all I ranging from 1 to n, right? Now what we already know something about the Pn minus 1, right? So what we know, that Pn minus 1 at xi, this is nothing but the yi for all I ranging from 0 up to n minus 1. Okay, so what can we say about the Cx then? So if we call this as, let me give the equation numbers. So I will require this later. So this is 1, 2, 3, and let's call this as 4. Okay, so what we have from the equation number 4, that Cx, which is the same as Pnx minus Pn minus 1x. So if I evaluate Cx at the xi's, where I is ranging from 0 up to n minus 1, so what will happen? So
0.
this is also an interpolating polynomial, and this is also interpolating polynomial. So I'm taking up to only n minus 1. Okay, so this is going to be 0 because both will take the same values. So at least I can get some idea about the polynomial Cx now. So Cx is vanishing at x0, x1 up to xn minus 1. This means that these are going to be the root of the polynomial Cx, right? So I'm going to have the factor as x minus x0, x minus x1 up to x minus xn minus 1 in Cx. right? Now, what more I can have here? So are these the only factors, or additionally we can have something here? So note that Cx is a polynomial of degree n, right? So this term itself, you can see that this itself is a polynomial of degree n, right? So it makes we can have some constant here, right? Let's call that constant to be n. So we cannot have any polynomial of degree greater than equal to 1 here, because we are seeking Cx as a polynomial of degree n. Okay, so an is a constant here, and which we have to determine. And how do we determine that? So we know that we are left with one condition here. So we want that Pn at xn should be yn, right? So I'm going to determine this coefficient. Such that when I evaluate Pn at xn, this will be yn. Nothing but f of x. So here the f of xi. Okay, so let's use this. So what I will get from the equation number 4 again. So I'm going to substitute x is equal to xn there. So I will get it as fxn. This equals Pn minus 1 at xn plus an times
x minus x naught.
xn minus x naught, and all the factors up to xn minus 1. Okay, so this gives us that an is f of xn minus Pn minus 1 evaluated at xn divided by xn minus x naught, and the product of all these factors, the last factor in this product is going to be xn minus 1. Okay. The nth order Newton's divided difference. So it will be clear in a while that why I'm calling it as a divided difference. So there's a justification for that. But this coefficient, we call it as the Newton's divided difference, nth order divided difference. So how this order, this is determined by how many points you're having here. So you're having x0 up to xn minus 1 and xn. So that's why the nth order divided difference. A formal justification for this. And what we denoted by, there's a notation used for this. So we denoted by f of x naught, x1 up to xn. So remember this bracket notation I used in the previous section also. So this an is this. Okay. So with this notation, I can write down my polynomial as, so Pnx is going to be Pn minus 1x plus, and we have found the explicit form of the polynomial Cx, because we have determined the constant also and we have the polynomial also. So this is going to be divided. Okay. So this is what we have obtained. So let's give it equation number. So this is equation number 5. So note that this is again an interpolating polynomial, right? which interpolates the data xi, fxi, I is ranging from 0 up to n. And we all the Lagrange form of the interpolating polynomial. So we are just aiming to get more insight about this term, that what this term exactly is, what are the properties this nth order dividing difference has. So for that, I'm going to compare it with the Lagrange form of the interpolating polynomial. So what do we have? The Lagrange form of interpolating polynomial is given by so we have summation with j ranging from 0 to n Ljx times f at xj, and where these Ljs are product 0 to n I is not equal to j divided by the product of
Ma'am, your
xj
voice
minus.
is breaking.
Yes, ma'am.
Yes, ma'am.
Yes.
All right, so let me just try changing the network which I'm using. Okay, is it better now?
Yes, ma'am.
Okay. So we have this form of the Lagrange. So this is a form of Lagrange interpolation. So I'm just going to do a little simplification here. So note that in the numerator of the LGX, we have all these factors x minus xi's, right? So I'm going to define a function psi n x as, so this is a polynomial, and this polynomial I'm just taking all these products, x minus x naught, x minus x1, up to x minus xn. Okay, so now you have to tell me what happens if I take the derivative of the psi n prime, the psi n, and evaluate it at say xj for some fixed j. So what I will get as an output?
All terms will be zero, only one term will remain, that is xj minus x naught, xj minus x1, dot dot xj minus x.
Right, so you can note that you will differentiate this term. It's like you will be applying the multiplication rule here. So you will be differentiating each term every time, right? So when you're going to substitute x is equal to xj, all the terms will be zero except the term which will arise upon the differentiation of x minus xj, right? So this is what we are going to have as an output. So we will have xj minus x naught, xj minus x1, and xj minus 1, and then the next term will be xj minus xj plus 1, and this will go up to xj minus xn. Okay, so using this new notation psi nx, I can write my ljx as, so how can I write my ljx using this psi nx and psi n prime of the xj? So can we use this to get a new form of the ljx? So note that the numerator is nothing but psi nx divided by x minus xj, right? And denominator is nothing but psi n prime of
X.
j. So therefore, what we can write the Pnx as summation j is equal to 0 to n. Ljx is psi nx divided by x minus xj into psi n prime of xj into f of h. Okay, So let me just write the constant term separately. So this is a function of x, and then we have x minus xj, and if xj divided by sine prime of the xj, this is the constant term here. Okay. So now what I'm going to do, so let's give it equation number 6. So we have obtained the form of the interpolating polynomial here also. So this is also the interpolating polynomial, interpolating the same data, right? And this is also the interpolating polynomial, which is interpolating the same data. That's why I'm using the same notation p and x for both, because actually both are the same polynomial. It's just that we have a different representation of them. Okay, so since both are the same polynomial, what I'm going to do, I'm going to compare the nth degree term. So from the equation 5, we will have the coefficient of the x raised to power n. And then from this expression, I can find the coefficient of the x raised to power n. And they both have to be same, right? Because both are the same polynomial. So what is the coefficient of x raised to power n from equation 5?
Divided difference if x naught or xn.
Yeah, so this is nothing but this nth order divided difference which we have found. Okay, so what we are doing basically, we are comparing nth degree term in Lagrange and in Newton's formula for interpolating polynomial. And what do we get? So from equation 5, we get it as f of x naught, x1 up to xn. And what we get from the Lagrange form? So note that this phi and x, this is so basically the polynomial part will be coming from this term, right? So if you will try to see it each term for different value, for some fixed value of the j, so the complete term you will have that x minus xj factor will be cancelling out, and you will be getting a polynomial of degree n on the numerator, right? So the coefficient of the x raised to power n is just going to be this term, this constant terms. So that is what do we have? We will get it as f of xj divided by sine prime of the xj, and sum over j is equal to 0 to n. Okay, so upon comparing both the forms, this is what we have got. So let's call this as 7. So using this formula, I can derive one property of these divided differences. So let's see some properties. Of this nth order divided difference. So first property, I'm just going to observe using this formula which we have obtained. So note that what do we have? The right hand side is this summation. So let me expand it. Right? So now if I change the position of these xi's here, suppose instead I consider a new set, let's call it I0, I1, and In. This is a new arrangement of these indices 0, 1 to n. Okay, So this is, let this be some permutation of this indices, this set 0 up to n. Then what can we say about this summation? So if I consider the summation over f of xij divided by sin prime xij, and j is ranging from 0 up to n. So what can we say about this summation? So what is happening? I'm just changing the order of these xi's, right? So for example, here I'm having x0, x1 up to xn, right? Now, if I just change the order, I suppose write this term first and this term second. So the summation is not going to change, right? If you arrange these, so here the order of the indices is 0, 1 up to n, right? Now I'm just rearranging them in a different order, say I0, I1 up to In. So what will happen if you are look into the summation? This is not going to change by the rearrangement of the indices, right? So this is going to be the same as f of xj divided by sin prime of the xj. J is ranging from 0 up to n, right? So it doesn't matter which order you sum the indices, whether you sum first, take this index as this term as first and then sum the rest, or you take this term as a first and then sum the rest. So whichever order you will have it, the summation is not going to change. Okay, what does that imply? If I look at it in terms of the divided differences, so this says that if we consider the n divided difference of x0 up xn, x1 up to xn, this is going to be the same as the nth order divided difference of f of xi0, xi1 up to xin, where this I0, I1 up to in, this is nothing but a new arrangement of the same indices 0 up to n. Okay, so this is called the symmetry of the nth order divided differences. Is this okay?
Yes,
Okay,
Yes,
so
ma'am.
second property, what we are going to observe is that these nth order divided differences so this is given by, so I can write this as the difference of two n minus 1th order divided differences, so which are going to be f of, so I'm going to take the last n indices x1, x2 up to xn minus, and then I'm going to take a first n indices, so these are going to be f of x0, x1 up to xn minus 1 divided by the difference of first and last index, which is xn minus x0. Okay, so let's try to observe that how can we obtain this relation. And this is the formula which we are mostly going to use in computing the divided differences. Okay, so we'll see in a minute while we will discuss an example. So let's first try to obtain this formula for the divided differences. So we have already observed that this side, this is nothing but a coefficient of x raised to power n in the interpolating polynomial, right? So likewise, this is going to be a coefficient of some interpolating polynomial, coefficient of x raised to power n minus 1 in some interpolating polynomial. And same with this, right? So if we want to prove that these both the terms are same, it's just that we have to obtain a relation between the interpolating polynomial, right? So what we are going to show, that if we take the nth a polynomial, interpolating polynomial of degree less than equal to n, this is going to be the same as xn minus x times polynomial of degree less than equal to n minus 1. But what is the data I'm taking? I will be taking the indices from 0 up to n minus 1. And then I have this term x minus x naught times again an interpolating polynomial of degree n minus 1. And it takes the indices from 1 to n and divided by xn minus x naught. Now, what are these polynomials here? Let me write explicitly. This is a polynomial of degree less than equal to n minus 1, which interpolates the function fx at these nodes. So we have x naught up to xn minus 1. So that's what I'm having in the superscript, I'm having 0 up to n minus 1. Okay, so likewise, this is an interpolating polynomial of degree less than equal to n minus 1. And what are the interpolation conditions? So we are going to have the interpolation data as so here I will have x size, f of x size, I is ranging from 1 to n. Okay, so that's why I'm writing here in the bracket 1 to n. So it will interpolate x1 fx1 up to xn fxn. So this will yield a polynomial of degree less than equal to n minus 1. Okay, so let's try to see that how can we obtain this claim. So what do you think? What should we do? So we already know that this is an interpolating polynomial. For this data, polynomial of degree less than equal to n for the data xi, fxi, I is ranging from 0 up to n. Right? So what should we do to prove this relation that both the polynomials are same? So whenever you have to prove that an interpolating polynomial is equal to another polynomial, it always what we have for the interpolating polynomial, we have already proved that there's only one interpolating polynomial, right? That is, we have a uniqueness of the interpolating polynomial. So if we are saying this is an interpolating polynomial, if we can also prove that this is another interpolating polynomial for the same data, then what do we have by the uniqueness properties?
Comparing the coefficients.
So, but as a polynomial, they both have to be same, right? If this interpolates the same data and has a polynomial, has a degree n less than equal to n, and if this also interpolates the same data and has a degree less than equal to n, then by the uniqueness of the interpolating polynomial, they both have to be the same polynomial, right? So this means that both are going to be equal. So what suffice to prove that if we define the right hand side by a new polynomial, let's define it to be qx. And if we can show that Qx is a polynomial of degree less than equal to n, which interpolates fx at the nodes x naught up to xn, then we are done, right? Because then this equality will follow from the uniqueness of the interpolating polynomial. Are you all agreeing with this?
Yes, ma'am.
Okay, so what we have to show that this is an interpolating polynomial. So what we are supposed to do now? So this is an exercise for you to check it out that this is an interpolating polynomial, and it just suffices to check because you can already observe that this is a polynomial of degree less than equal to n minus 1. This is a polynomial of degree less than equal to n minus 1, and you are multiplying a factor xn minus 1 x, and here you are multiplying a factor x minus x naught. So this will make it as a polynomial of degree 1 higher, right? This is also going to, you're just multiplying a linear polynomial. So altogether, Qx is going to be a polynomial of degree less than equal to n, right? So only condition which you have to check whether it is interpolating fx at this point or not. That is, you have to check that if you evaluate q at xi for all I ranging from 0 up to n, whether this gives you fxi or not. Okay, and of course, since I'm claiming that this is going to be an interpolating polynomial, so you will be able to obtain this. So you just have to observe it for all different xi's. Okay, just substitute here and use that this pn minus 1 x here, these are the interpolating polynomials, and you will be able to observe this. Okay, so once you will prove this, then by the uniqueness property of interpolating polynomial, we are going to have that Pnx has to be the same as Qx. Okay, and Qx is nothing but the polynomial which we wanted Pnx to be equal to. Okay, so we have obtained this. Now it's just about comparing the coefficients from both the polynomials. So comparing the coefficients of x raised to power n from Pnx and Qx. What do we get? So from Pnx, we are going to get f of x naught, x1 up to xn, the nth order dividing difference. And what I will get from this polynomial in the right hand side? So Pn minus 1 is a polynomial of degree less than equal to n minus 1. And I want a coefficient of x raised to power n. So I have to see that it will multiply with this x here, minus x here. Right? The highest order term in this Pn minus 1, 0 and minus 1, when you will multiply it with the minus x, then you will get the coefficient of x raised to power n from here. Right? And what is going to be that coefficient? So it is going to be f of x naught. So I have a data from 0 up to n minus 1, right? So I will have it as x naught, x1 up to xn minus 1 with the minus sign, because I'm multiplying it with the minus x here. So likewise, if you observe from the second term, from here, the highest order term, which is the coefficient of x raised to power n minus 1, that is going to be f of x1, x2 up to
xn.
And in the denominator, we have it as xn minus x0. Okay. So this means that you can compute the nth order divided difference using the n minus 1th order divided difference. And if you observe this formula in the right hand side, so you have a difference of two quantities in the numerator and difference of two quantities in a denominator, right? So it's a division of two differences. So that is the reason we call it as a divided differences. Okay, so this also explains the name. Divided differences. Okay. So we have observed certain properties of these divided differences. So finally, what we have got the P and X as the Newton's form. So let's look back again. So we have got the form as this, right? So from 5, we have this as Pn minus 1x plus x minus x naught up to x minus xn minus 1 times nth order divided difference of f at x naught. Okay, so let's write down like how the polynomials looks like. Say the what will happen for the case n is equal to 0. So what is going to be p0 of x? So p0 of x is just a constant, and that constant is going to be simply f of x naught. Okay. Now what is going to be p1 of x? We can use this formula here. So p1 of x is going to be p0 of x plus x minus x naught divided difference, first divided difference of
X not x1.
f at x naught, right? And what is going to be p2 of x? P2 of x, you can write it as it is going to be p1 of x. P1 of x is p0x plus x minus x naught, f x naught x1, and then the next term will be x minus x naught into x minus x1 divided difference of f at x naught x1 x2, right? So likewise, you will be able to write the Pnx. So this is going to be Pn minus 1x plus this term, right? But we already have the expression of the Pn minus 1x as well. So which is P naught of x. P naught of x is simply f of x naught plus x minus x naught. First divided difference of f at x naught, x minus x naught, x minus x1. Second divided difference of f at x naught. And this, the last term is going to be x minus x naught, x minus xn up to x minus xn minus 1 times the nth order divided difference of f at x naught. Okay, so this is called the Newton's divided difference formula for
Interpolation.
Interpolating polynomial. Okay. So what is important to find this polynomial using this formula? That you have to compute these divided differences, right? So let's just take one example and try to find that how do we compute these divided differences. So I'm going to construct the divided difference table. for the function. So let's take a simple function. So I'm going to take fx is equal to x. Okay, and the data which I'm taking as, so since I've given the function explicitly, I just have to give the x size, right? So x size I'm taking it as, so let me take 1, 2, 3, 4, and 5, some simple indices. So then I will have fxi. Okay, so this is going to be 0 here. So let me take x squared here. Okay, and let me go up to just 3, or maybe I can go up to 4. So here I'm going to, so let me start with 0. So I will have it 0 and then 1. We'll have, yeah, this is okay. And 4, 9, 16, right? And we have to compute the divided differences using this data. So let's compute the first divided difference. So, okay, let me use a shorter notation. So for dr of fxi, this is nothing but f of xi plus 1 up to xi plus r. So this is the rth order divided difference of f at xi. So I'm just using this as a notation, okay? So that I don't have to write the complete this big expression every time. So I'm going to find the first divided difference of f at xi. So what it will be? How will I compute? So you look at the formula. So I have to, if I observe what is f of x0, x1, for example. So this is going to be f of x1 minus f of x0 divided by x1 minus x0, right? For that matter, if you have any of the xi and xi plus 1, this is going to be f of xi plus 1 minus f of xi divided by xi plus 1 minus xi, right? So basically, I have to take a difference of these two consecutive entries and then the difference of these two consecutive entries and then take a division of that. That is, this difference is divided by this difference. So what I will get, 1 minus 0, 1 divided by 1 minus 0. So this is going to be 1. And then 4 minus 1, 3 divided by 2 minus 1. So this will be 3. And then 5, then 7. Okay. So likewise, I can compute the second order divided differences at xi's. So what is the second order divided difference? So if I consider f of x0, x1, x2, so this is going to be by using the divided difference formula. So this will be f of x1, x2 minus f of x0, x1 divided by x2
x2 minus x0.
Right? So I have already computed the first order divided differences, right? This is nothing but, so with these two indices, so this is f of x0, x1, right? And this is f of x1, x2, like that, right? So if I have to compute this, I'm just going to take a difference of these two indices and then divide by the, so these three nodes this time, so divide by the difference of the
2
x2,
minus 0.
right? So what I will get, 3 minus 2 divided by 2 minus 0. So this is going to be 1, right? So I'm just going to repeat that. So 5 minus 3, 2, and then, so this will be 2, no, sorry, 3
1.
plus 1, 2. So this will be 1 again. And then again, here also you will get 1. Okay, so now you can find the third order difference, divided differences. So here, how will you find it? You have to take a difference of these two. And here you will take a difference of 3 minus 0 here. Okay, so this is going to be simply 0 because The numerator is 0. 1 minus 1 is 0. And likewise, this is going to be 0. Okay. And the next divided difference, this is also going to be 0. Because both the numerator is 0 here. Okay. So this is how you construct the divided difference table. Okay. So once you have these divided differences, you know that what you require now. You just require f of x naught x1, f of x naught x1 x2, and all these indices, right? So basically they are, so f of x naught x1 is this, f of x1 x2, x naught x1 x2 is this. So basically these are the entries which we will be requiring to form the Newton's interpolating polynomial. Okay. So now let me give one example. Sorry, exercise. So you can construct the divided difference table for the function fx is equal to, you can take any function. So either you can take x cube, or you can work with the, or say you can also consider the fx is equal to root x. Okay, and you can take the x size as, so let me just write it in the form of the table. So the values of the x size which you can consider. So you can take it from 1, 2, 3, 4. So x naught, x1, x2, x3, and x4 is 5. Okay, you can use the calculator if needed. All right.
Yes,
So
ma'am.
once you have constructed this table, of course, it is too easy to just find the polynomial. You just have to use this formula, and then you have to substitute the divided differences which you will be finding from the table. All right. Now we have found a new form of the interpolating polynomial, right? So we can also obtain the error formula using these divided differences. So this is an error formula, so interpolation error formula. Using divided differences. That is, we have already obtained the Lagrange interpolation error formula, right? So I'm just going to obtain a new formula for the interpolation error. So we will be given the data x naught up to xn, and we have the functional evaluation fxi on those data. And suppose we have to compute the error at the point t. Okay, let t be any real number distinct from the node points x naught, x1 up to xn. Okay, and what we are aiming? We want to see that what happens to ft minus pnt, right? This is going to be the interpolation error at the point t. So for that, what we are going to do, so we are already given this n plus 1 nodes. So I have one additional point t, right? So I'm going to write an interpolating polynomial which interpolates the complete data, that is these n plus 1 points together with this point t. Okay, so the interpolating polynomial of fx at the nodes x0, x1, xn, and t is given by interpolating fx as, let me write this way, then the polynomial interpolating fx at these nodes. This is given by, so what will be the degree of that polynomial? So how many points we have? We have a n plus 2
N.
points, right? So this
Yes,
is
ma'am.
n plus 1x. So let me denote by Pn plus 1x. So I'm just going to write the Newton's form of the interpolating polynomial. So this is going to be f of x naught plus x minus x naught, f of x naught x1. And this goes up to, the second last term is going to be x minus x naught up to x minus xn minus 2. No, sorry, xn minus 1, because we all have n plus 1 data points. F of the divided difference of f with the arguments as x0, x1 up to xn. And the last term is going to be x minus x0, x minus x1 up to x minus xn. And the divided difference will be at the nodes x0, x1, xn, and then t. Okay, so basically up to here, this is nothing but the pnx. So this is pnx plus x minus x0, x minus x1 up to x minus xn into n plus 1th order divided difference at the nodes x0, x1, xn, and t. Okay, so this is what we have as pn plus 1x. Now, what is the property I have for this pn plus 1? That this interpolates fx at the node t also, right? So this means that I have that pn plus 1 evaluated at x is equal to t. This is going to be what it is going to be?
f of t.
So this will be f of t. So therefore, if I take x is equal to t in this equation, whatever I will get? I will get this as, so pn plus 1 t, which is the same as f of t. So this equals pn evaluated at t plus t minus x0, t minus x1, t minus xn multiplied by the n plus 1th order divided difference of f at these nodes. Okay, so from here, what I have got, that ft minus pnt, this is nothing but t minus x0 up to t minus xn times n plus 1th divided difference of f with these arguments. Okay, and this is nothing but the interpolation error, right? ft minus pnt. So this is what we wanted to compute. So this is the another formula for the interpolation error, but what we have obtained this using the divided differences. Okay, so this is the interpolation error. All right, and what is the interpolation error formula we have obtained using the Lagrange interpolating polynomial? So can you tell me? So we had ft minus p and ts. It was the same factor, t minus x naught, t minus x1 up to t minus xn divided by factorial n plus 1 into n plus 1th derivative of f evaluated at some xi, where xi lies between the smallest interval containing all these nodes. Okay, so if I compare these two formulas, so if I call this as, so what is the equation number I have? Okay, I think this is 8. And let's call this 9. So note that both are the same formulas, right? Because Pn is the same in both the cases. So if we compare eight and 9, what we obtain that this term, which is f of x naught, x1, xn with t, this is going to be the same as n plus 1th derivative of f evaluated at some xi divided by factorial n plus 1. For some xi is in the smallest interval containing x naught up to xn and t. Okay, so just for the notational convenience, if I call this t as xn plus 1, because I already have the nodes up to xn, so I'm just going to call this as a new node. Okay, and then if I replace n plus 1 by m, so what I will get the formula as, I will get this as x naught, x1 up to xm. This is going to be same as the n plus 1. N plus 1 is m. Xi divided by factorial m. For some xi is in the smallest interval containing all the xi's. Okay. So this is the formula which I had used in the previous section in proving some of the convergence results. So basically what it says that mth order divided difference of the f is related to the mth derivative of the f at some point xi. Okay. So this formula is going to be useful at different places. So we'll see that how we make use of this formula. All right, so now if you observe, let's look back again these formula which we got for the divided differences. So basically this is the main formula which we have been using to compute the divided differences, right? So one thing you can observe from here that I have been taking the nodes as a distinct nodes. That is all the nodes xn minus xn and x, all the xi's are distinct, right? But these divided difference formulas, I can see it independently of the, so given any node x naught, x1 up to xn, I can really form this difference and take the divisions, and I can talk about the divided differences, right? So but these formulas are not going to be valid if your any of the two nodes coincide. Suppose you have two data points, say x1 and x0 and equal to x1, then you will see that in the denominator you're going to have the terms like x0 minus x1. So these terms are not going to make sense for the cases when these nodes coincide. Okay, so this means that this formula which we have got here, this is not useful in the case of the when we have any two equal nodes, or say you have many say 4 nodes which are coinciding. So this formula is not going to be useful in that case. So now we are going to see another formula for the divided difference, which can be used even when the nodes coincides. Okay, so first let's obtain the formula, and then we will see that how this is going to be useful. So this is, I'm going to prove this as a theorem, and this is due to the Hermite and Genuli. So what this theorem says, that suppose I have n plus 1 nodes, x0, x1 up to xn, be distinct, and let the function f be n times continuously differentiable on the interval. So I'm going to consider the interval, the smallest interval containing all these nodes. So which is h, x0, x1 up to xn. So this is the notation I've been using for this interval. Then the nth order divided difference of f at x0 is given by, so I'm going to compute it using this integral. So I'm having this integral over a region tau n, and this is the integral of the nth derivative of f evaluated at t0 x0 plus t1 xn, and this is up to tn xn, and this is the integration with respect to the indices t1, t2 up to tn. dt1, dt2 up to dtn. Okay, so that is, we are taking a nth derivative of the f, and with these arguments I'm going to integrate it with respect to t1, t2, tn. And now what is this region tau n here? Where this tau n is this region, it is a set of all those t1, t2 up to tn, such that each of these ti's are non-negative, and if we sum the ti's from I is equal to 1 to n, this is less than equal to 1. Okay, so this is the reason tau n, and note that I have not defined what is t0 so far. So this just includes t1 up to tn. So what is t0? So t0 is 1 minus summation of ti's, I ranging from 1 to n. Okay, so which means that I have that summation of all the ti's, I ranging from 0 to n, this is equal to 1. Okay. So let's just try to visualize this reason tau n, okay, which then it will be easy for us to prove this theorem. So what is tau 1? Can you tell me? So what is tau 1? Tau 1 is the set of all t1 such that t1 is greater than equal to 0 and t1 is less than equal to 1. So this is going to be the interval 0 to 1. Okay. And what is going to be tau 2?
T1 comma T2.
Such that your
T1 T2 greater than equals to 0
t1 and
T1 plus T2 less than equals to 1.
So can you visualize this reason? What is this reason? If I take the t1, t2 plane, so what is this reason tau 2? So basically, if you draw this line, T1 plus T2 is equal to 1, this is this line. Right? And you have that T1 is greater than equal to 0. So basically, in the positive quadrant, you're going to have, this is your reason tau 2. Okay. So likewise, tau 3 is going to be just a pyramid. If you have one more axis here in the T3 axis, and there also you will have the height 1. Okay, so it's like a pyramid here. Okay, so this is how the these reason tau n can be visualized. All right. So now let's try to prove this theorem. So I'm going to use the principle of mathematical induction to prove it. So we prove this theorem by induction arguments. So for that, we have to see what happens to the base case. That is, let's take the case n is equal to 1. So first we prove that, so I have to give it a equation number. So I think 8, 9. So let's give this as 9, and this is at 10. And this is at 11. So first we prove 10. First we prove that the 10 holds for n is equal to 1. Okay, so so what we are supposed to prove, we have to show that f of x0, x1, this is the same as that if we evaluate f n is equal to 1 here, so f prime of t0 x0 plus t1 x1 dt1, so this is going to be the same as this. Okay, so I'm just going to consider the right hand side. So let's just take the right hand side. Sorry, we just have one integral here because we are in the case n is equal to 1. So what is the reason tau 1 is nothing but the interval 0 to 1 f prime, and t0 is, what is t0? Is 1 minus t1, right? So t0 x0 plus t1 x1 dt1, this equals 0 to 1 f prime. I'm substituting t0 is equal to 1 minus t1. Okay, so I'm just doing some simplification. So I'm just combining the terms with the t1. So I will get x0 plus t1 times x1 minus x0 dt1. Okay, so I can simply integrate it. So upon integrating, so we are having a derivative here. So if I integrate it, so what I will get f of x0 plus t1 times x1 minus x0 divided by x1 minus x0, because I'm integrating with respect to the variable t1, and the limits are going to be 0 to 1. So if I substitute t1 equal to 1, what I will get? F of x1. And if I substitute t1 is equal to 0, I'm going to get minus f of x0 divided by x1 minus x0. So this is nothing but the first divided difference of f at x0. Okay. So thus the result holds for n is equal to 1. So now what we have to do? So we will assume that the result holds for the case, say n is equal to k, and we'll try to prove it for n is equal to k plus 1. Okay. So now we assume that the equation 10, this holds for n is equal to k, and prove it holds, prove that it holds for n is equal to k plus 1. Okay. So for n is equal to k plus 1, again I'm going to consider the right hand side. So that is, I'm going to consider this integral. So the reason of the integration is going to be tau k plus 1 and k plus 1th derivative of f evaluated as t naught x naught plus t1 x1 up to tk plus 1 xk plus 1 dt1 dt2 up to dtk plus 1. Okay. So note that we have already assumed that the result holds for n is equal to k, right? That is up to the tau k. We already know that how the integrals are related to the divided differences, right? So, but here I have a one more variable of the integration, which is tau k plus 1, right? So what I'm going to do, I'm just going to integrate with respect to the tau k plus 1 so that it will reduce the things to the tau k, and then I'll try to use the induction assumption. Okay. So for that, I'm just going to do the change of variable here because I want to integrate first with respect to tk plus 1. So I'll change the order of the integration. So note that. So again, I will come back to the case of the tau 2 to explain it. So here, if I have the suppose integration with the limits dt1, dt2. So what are going to be the limits for the t1 and t2? Suppose here to or 2.
T1 goes to 0 to 1 minus t and T2 goes to 0 to 1.
Right. So T1 will go 0 to 1 minus T2, and then T2 will go from 0 to 1, because when you will integrate it, you take any strip here. So you can see how this strip behaves. So this is going from, sorry, so we are integrating first with respect to T1. So we will have the strip
Horizontal.
So you will take this as an strip, and you can see this is ranging from here T1 is equal to 0, and on this line T1 is equal to 1 minus T2, and these strips vary from 0 to 1. In the range, T2 is varying from 0 to 1, right? Now if I want to change the order of the integration, so what will be the new limits? Suppose I want to integrate with respect to T2 first and then T1 first. So you will take the strip of this form, right? So here again T1 will go from 0. Okay, first I want to integrate with respect to T2. So T2 is 0 here and T2 is 1 minus T1 here, 0 to 1 minus T1. And then these strips will vary from 0 to 1. So this is how the limits will change if you change the order of the integration, right? So I just want to integrate with respect to tk plus 1 here, right? So I just do the limits for the. So I'm taking the region tau k, I'm keeping this as it is. I'm just keeping the limits for the k plus 1. Okay, so this will go analogously as you have observed for the case of the 2. This will go from 0 to 1 minus t1 plus t2 up to tk, and I will have the complete this term. So I'm substituting t naught is equal to 1 minus summation of ti's I is equal to 1 to k. Okay. So what I will get x naught and then each of the ti will be multiplied by x naught. So I'm just going to simplify this term. Note that there's no bracket here. So we will get this as t1 times x1 minus x naught. The last term is going to be tk plus, sorry, this is k plus 1. Tk plus 1 times xk plus 1 minus x naught, and then dtk plus 1. So this I'm integrating, and then I'm having the integration over the variables on top. Okay. So now I'm going to integrate this. With respect to tk plus 1. So what will happen? I will have the integration over the tau k. So I have the k plus 1th derivative of the f. So it will be reduced to the kth derivative of f. And I'm integrating with respect to the tk plus 1. So I will get the factor as 1 divided by xk plus 1 minus x naught. Right? And then fk will be evaluated as x naught plus t1 x1 minus x naught up to tk plus 1 xk plus 1 minus x naught, and the limits of the tk plus 1 is, this is 0 to 1 minus t1 up to tk. Okay, and then this complete thing is integrated with respect to these variables. Okay, so now let's substitute the limits of the tk plus 1 here. So when tk plus 1 is equal to 1 minus t1 up to this, when we'll substitute this, so I'm just going to simplify this. You just observe this step whether these are correct. So I have the factor xk plus 1 minus x naught, and then I'm substituting tk plus 1 is equal to this factor. So I'm going to combine the term with all the ti's. So I have xk plus 1 minus x naught, and then x naught is sitting here. So x naught will be cancelling out. So I will be left with the xk plus 1 plus t1 into x1 minus x naught, and then minus xk plus 1 plus x naught. So I will have this as t1 times x1 minus xk plus 1. So likewise, the last term is going to be tk times xk minus xk plus 1. Okay, and now minus, when I will substitute tk plus 1 is equal to 0, I will get this as fk x naught plus t1 x1 minus x naught, and the last term is going to be xk minus x naught times dt1 up to dtk. Right? So note that I have reduced to the tau k, and here the derivative, I have it with this the kth derivative of the f. So I can use the induction hypothesis. So I will have the 1 by xk minus x naught factor outside. So if I use the induction hypothesis, what the first term will be equal to? So this will be equal to f divided difference of f with respect to the, so I will start with the index xk plus 1, and see, you have to see what you have to have in this form, right? So I'm considering f of x naught x1 up to xn. This is nothing but in the, if you see in the argument, I just have t naught times x naught plus t1 times xn plus t1 times xn, right? So I just have to see what are the arguments I'm having here. So note that I'm going to combine all the xk plus 1 terms, right? And then I'm going to for the torque, T naught is going to be 1 minus summation of Ti, I is equal to 1 to K. Right? So I will get T naught xk plus 1 plus T1 x1 up to Tk xk. So what are the indices I'm going to get it here? Not these. Right? And same thing if I observe from here, this is going to be divided difference of f with the arguments starting from x0, x1 up to xk. Okay. Now still this is not in the correct form. So what I'll do, I'll use the symmetricity of the divided difference in this term. So I'll just exchange the I'll bring this first, okay, and I'll take this xk plus 1 to the end. So x1, x2 up to xk plus 1 minus f of x0, x1 up to xk divided by xk plus 1 minus x0. So this using symmetry of divided differences. Okay, and if you observe, this is nothing but the k plus 1th divided difference of f with the indices this. Okay, so this means the result holds for n is equal to k plus 1, and therefore by the principle of mathematical induction, the result is true for any natural number n. So let me write all n is in. Okay. So if you have any doubts here, you can ask now.
Formula is also only valid for distinct data, like x0, x1, x2 should be
Yes.
distinct.
I have not commented anything about what. So this formula I have opted when all the sides are distinct. Okay, but if you try to observe this formula,
No, you are not audible properly.
yes, is it okay? Is it better?
Yes, ma'am.
Okay, so since you have asked, let me just point it out. So we have obtained this formula, right? Now if you try to observe the right hand side of this formula, so this is going to be valid even if you have some of the indices are going to coincide. Okay, so this integral is not going to like in the case of the when we had the definition of the f, the dividing differences in the form of the different the divisions. If the denominator is going to 0, then divided differences are not going to make sense, right? But using this new formula, even if some of the indices are going to coincide, that is if you or some of the xi's are going to coincide, this you can use the right hand side of this equation 10 to compute the divided differences. In fact, you can try to find it, or we will see it in the next class, that if you try to observe, you take all the indices xi's the same as x0. Okay, so what you can find, so here I'm taking this as n plus 1 indices here. Okay, so this is going to be fn naught nth derivative of f evaluated at x0 divided by factorial n. So you can prove this using the Harnaut-Janicki formula. Okay, so you work it out, or we will see it in the next class.
But ma'am, in the proof we are using that x0 is not equal to xk plus 1.
Yes, so that's what I'm telling. We obtained the formula for the f, the divided differences, right? And this formula, if you see it the right hand side, if I'm not seeing it as that these fxi's are not going to make sense for the case when you have in the form of the divisions, right? In that case, you have that you cannot use that formula to compute the divided differences. But if you try to see this formula, this does not violate anything, even if you take some of the xi's which are equal, right? So what I am trying to say here is that this formula is going to be valid even if your sum of the xi's coincides. Okay, so here I used when I'm deriving it, of course, I took this assumption. Where is the statement? Yes. So here, while deriving this formula, I consider that these are the xi's are distinct, right? When I obtain this formula, now when I'm looking at this formula, that is the right hand side of this equation 10, so this perfectly makes sense even for the xi's which are going to be same. Okay, so the message what I'm trying to convey from here is that if your sum of the xi's are going to coincide, you cannot use the difference formulas, that is the division of the two differences. Okay, but this formula is very well suited even if your xi's are going to coincide. All right, so we stop here since I have another class. So we'll discuss it in the next class if there are any more doubts. Okay.